So what happens when we don't have a right triangle and we are trying to solve the parts? We can use either law of sines or law of cosines. So 7.1 from our text deals with a law of sines. And if we think back to geometry when we first talked about triangle congruences, we had 4 shortcuts. So we didn't have to know that all 3 sides and all 3 angles between the 2 triangles were congruent. It was enough to know just the 3 sides. That in turn locked the angles into place. And so I knew that the triangles were congruent. So that's what side is, SSS. Side angle side means 2 sides with the angle at their meeting vertex, so the one that creates them. Or angle side angle is 2 angles with the included sign. So the side and then essentially the angles at each endpoint. Or I could have had 2 angles in a side, and the side didn't have to be in between. It was not an included side, and that would still, in fact, work for me. So what we have with the law of sines, which is written here below, if we jump ahead a little bit, the very quick explanation for deriving it. If you look at my triangle ABC, I drew in the height. So that altitude goes from the vertex perpendicular to the opposite side or line containing the opposite side. And so if I look at just my triangle on the left, so I'm looking at the sine of A. So opposite over B would be my hypotenuse. The sine of A is equal to hypotenuse, height over B. And when I solve for the height, I just have to multiply by B. If I do the exact same thing with triangle B, the sine of B, the opposite side is the height, and side A is actually the hypotenuse of that little triangle I've created on the right-hand side. Multiply both sides by A, the same thing happens. Well, if the height is equal to either B sine A or A sine B, I can set those two things equal to one another, and then just a little bit of algebraic manipulation. If you divide both sides by B, that eliminates the B from the left side, and then if you divide both sides by A, it eliminates the A from the right side, and we end up with these first 2 components of the law of sines. I could set it up again with a different height to introduce the sine of C over C instead. So it's the ratio of the sine of the angle divided by its corresponding side. So we're not thinking opposite, adjacent, hypotenuse anymore. We're thinking angle and corresponding side. And since it all involves the sine, it's the law of sines. What happens with this shortcut that did not work in geometry, and we always said it SSA, not ASS, side angle. The ambiguous case, the issue is, and you might have done some sort of exploration with this, we might get one triangle that works, and we can find then that height is B times the sine of A. It could fit perfectly into a right triangle. It could be too short where it doesn't work and we have no triangle, or it can be a side that can kind of hinge left or right, and we can create 2 triangles from it. So this is why it didn't work as a shortcut, because we couldn't guarantee that it created one unique triangle so that we knew that it was congruent to the given triangle. The ambiguous case we can practice all on its own for one day. Without practicing those, knowing we have some problems that do in fact create just one triangle. So the side length is greater than the height, and the side length A greater than the other side length B is really what we're focusing on here with just the one triangle. So if we want to find all of the missing parts solving each triangle, I'm going to take a look at number 10. So if I make a triangle that is 56 degrees and 24 degrees, that adds up to 80. It doesn't have to be perfect, but that means that my missing angle has to be the other 100 degrees in figuring that out. And so for number 10, I'm going to draw this obtuse triangle. It doesn't have to be perfect, but if I call this A and say that this not drawn to scale triangle, that I have 56 degrees there, and B I don't know, and C I can put up here at 24 degrees. And again, these do not have to be drawn to scale. But if I add 56 plus 24, that is 80 degrees. All triangles have to add to 180. So if I subtract 80 from 180, then I have 100 degrees left, and that is what angle B must be equal to. So in solving the first part, I have that it's exactly 100 degrees. So side A is opposite angle A. So my little a is my 22 over here. So it is important to use what I have. So because I have the 56 degrees and the corresponding side A, I have the sine of 56 divided by the given A, which was 22. I then can use either of the others first. So if I do the sine of 100 divided by B, because angle B will be opposite side B, that should be my longest sine. So it should be the longest between the 22 and then whatever C is, it'll be my biggest number. I can cross multiply this to solve. So if I multiply B times the sine of 56 and 22 times the sine of 100, and then divide, I have 22 times the sine of 100 degrees divided by the sine of 56 degrees. And I'm supposed to round to the nearest tenth. And so I should get a 26.1 for side B. Now, I really didn't need to set up all of the law of sines, all three parts together, because you can't cross multiply then when you have the three-part equation. So if I set up just the first two, and then I'm going to go back to my sine of 56 and my given 22, because these are exact measurements. I didn't have to do any rounding. And you know we don't like that round off error. So multiplied by the sine, equal to the sine of 24 degrees divided by multiply. So the 22 gets multiplied by the sine of 24. The C would have been multiplied by the sine of 56. So you have to divide both sides by the sine of 56. And so for side C, you should get 10.8. And again, whatever these units are, because we don't have the units listed. So the angle was pretty easy to find. If you have two, it's easy to find the third. That's just the triangle sum theorem, that triangles add up to 180. And then sides, it's just one at a time. So using the ratio that was given, basically these partners, because I had the 56 and its corresponding 22, I used the sine of 56 over 22, and then find B, and then find C. I can also use this to find a missing angle. So suppose I had one angle and the two sides, and that's what the ambiguous case gets into. You can take the sine of angle A divided by the known side A and have your other ratio set up, and then you just have to use the inverse to undo it. But all of these example problems have two angles and then one side given. So you're finding the one missing angle and the two missing sides. The other use for the law of sines, besides solving parts for non-right triangles, is that there's an area formula that's very easy for it. So from the picture we had up above, if we have the sine of A is equal to the height over B, whenever we are looking at the area formula, area is 1/2 base height. And so if my height is H, and this is referring to that image above, so it would be C times H, I can replace the H with the B sine A. It really works out so that whatever you have in terms of angle or sides, it's really like one of each. So if you have angle A, then you're going to have sides B and C that get multiplied together. If you have angle C, you have sides A and B. And then if you have angle B, you have sides A and C. So it always pairs that you will have one angle and then the other two sides in order to calculate the area. So if we take a look, just to practice one of these quickly, we'll look at 37 down here at the bottom. I have angle C, which is why it's capital letter, and then my two sides. So my area, not using a capital A because I don't want to confuse that with the angle A. Area would have to be 1/2 of AB times the sine of C. So if I were to create this triangle, B sine C is the height 1/2 base times height. My given measures, so that I can easily just substitute this in. So it's 1/2 of 4 times 6 times the sine of 124 degrees. And then it is, with all of these, making sure we had our calculators in degree mode. It should give us 9.94, and yay, I finally have units. This is meters squared because I'm calculating area. So again, a lot to the law of sines, but it is one way that we can solve for parts of triangles when they are non-right triangles and I'm unable to use SOHCAHTOA.